So, welcome back everyone. I'm thinking you're becoming better data scientists. I'm proud of everyone as much as they've come this far. And I would want to crown you all. So, continuation of self-organizing maps. I'm going to take you through the terms and then the processes that are very key and very, very vital to the self-organizing maps, the processes that you need to know, and then the algorithm. So, the terms that I used first is a vector quantization. This is when the data compression, it's more of a data compression technique, and it provides a way of representing multi-dimensional data in a much lower dimensional space. So vector quantization is a way of putting or lowering the dimensional space into either typically 1 or 2 dimension. As we well know that we said earlier on that with SOMs or self-organizing maps, we deal with 2 dimensions. So dimensionality reduction is done in 2D. And then we later talked about the neighborhood, as we are going to see that a neighbor tries to implicate the result of an SOM. I'll give you an example. Say, imagine you had your own social media network and you wanted to know which of them is actually important, because in a network, it's who you know, not who you are. I'll still take you back at the current pandemic. We all know that most of the times they do as such, they are searching for your contacts. Who is your neighbor? So the neighbor is the kind of person that you have interacted with. So just as any other network, neighborhood or determining a neighborhood is a very key important role. Then the output space, which will be our output, and then later our input space, which will be our X. SOMs basically deals with 3 processes, that is competition, cooperation, and adaptation. So with competition, we have seen people, any person or any race trying to compete among themselves and trying to know who of them best matches or who of them outcomes as a winner. So just like any other competition, or SOMs deals with competition. And it, as we have said before, it is a very, very competitive learning process. So the output neurons in a self-organizing maps compete with each other to best represent the particular input sample. So input space is put in, or input space is put in, which is your X, and then there is a determination of the weight, or how much input sample space is the weight. Then later there's a correlation, or there's trying to determine a relationship, which of them best outlines or best depicts the input sample. So that is when you determine the winner or the best matching input. So it is a simple process. You input your sample, do a computation of your weights or initialize the weights, then later differentiate or try to see which of the input sample space best matches the samples that were inputted before. Then there is cooperation. As we said, one of the properties that self-organizing maps possesses is a topological property. Self-organizing maps is a topographic organization in which nearby locations in the output space represents inputs with similar properties. So after we have done or outputted our best matching unit, we then later look around, and if we find a neighborhood that is in a nearby location that almost does have similar properties with the input sample, it stands a very high chance. So that's what I've told you. With similar properties, your neighbor matters, your network matters. So same as the With the self-organizing maps, it does cooperation. Then it later does an adaptation, which is more or less, we have seen, this is a picture trying to show you from where we came from to Stone Age to currently where we are, and we are seeing a man trying to adapt. So adaptation does the best weight vectors of the best matching units and its neighboring inputs into the map are adjusted in favor of the higher values of the discriminant function. We are going to look at the different discriminant functions, or we are going to look at the different distances that are put into consideration. Some use Manhattan, some use Euclidean, some use different vector space. All these are different distance calculations. So discrete function would align with the different adaptation methods. Then the big question is, how do SOMs work, or how do self-organizing maps work? The self-organizing maps are typically consist of two layers of nodes, the input layer and the output layer, as shown below. So you have your input, as we have seen before, which is your X. We have seen it before in the structure. And then you have your weight matrix that is attached to it, and then the output, depending on where classification will be done or clustering will be done best. And then I'll then later take you through the algorithm. So the algorithm is more or less a 6-stepped data. It's a 6-stepped process, and the different ways of one way, or the different times we have seen any first step with self-organizing maps is just initializing. You initialize the weights of the vectors. So you start with initialization, and initialization can go till to n-dimensional space, where I represents a set of 1 to n, and n denotes the number of output nodes in the network. As we have seen, we have nodes and edges in any network, and we feed it with input and we see output from the node of the network. Then the second step is done by determining the radius, or the second step to self-organizing maps is to determine which of those outputs, or which of your input samples have similar attachments or similar properties or topological properties of the sample in study. And then later, the third step is to determine or to find the best matching unit, which is called the BMU. The distances are always calculated on which of them possess the best properties. If I'm looking out of, say, of the airlines, which of them has the best or possess best properties based on what is put out there. And I'd said before, we have different types of distances. We have Manhattan, Euclidean, vector products, among others. But with self-organizing maps, it generally uses the Euclidean, where we find the triangular distance of a weight calculated from the output space. We always use the Euclidean distance. Then later, after you have calculated the BMU, you now calculate your neighborhood. Neighborhood comes with a radius, and also neighborhood comes with the similar properties, similarity of the best matching process, with an iteration done of the minimum distance. So I'm still going to take you through, as we go on, a continuation of the iteration, and I'll show you how to do it in our next slide. Thank you.